Hi, welcome to our course, one more lecture of the course, Fundamentals and Biomedical Applications of Quantum Science and Engineering. You know, in the last few lectures, we will be dealing with many different concepts. We learned an equation that for a physical system, it produces a wave function. And this wave function represents the physical system in some sense. And we have to extract from this function all the properties, all the physics going on, all the phenomena going on that system. And we have made an interpretation of this wave function. Of course, the wave function carries a lot of physical properties. In the wave function, we can get the main physical quantities like momentum, like energy, right? All this is in the wave function. Since we are talking about a massive particle, right, like an electron or a proton or a neutron or anything like this, or even non-massive particles like the photons. But we're going to deal with the photons later on. But then we learn the interpretation of this wave function, that the modulus square represents a density function, density of probability. So we learned that this wave actually is a wave of probability distribution that oscillates in time depending on the energy, because we learned that higher energy, higher time oscillation. And higher momentum, higher spatial oscillation. We learn all that. So we then have this master equation, the way we call. And this master equation allows us to analyze many physical situations. And from those physical situations comes many nice phenomena that is no equivalent in classical physics. So today we're going to start to apply this equation. In the few last lectures, we show the properties of this equation. We even show the fact that there are some interesting properties of the wave function, like it is continuous, and the derivative is continuous, because the derivative of the wave function is related to the momentum. So in a very, very, very specific situations, the derivative will be discontinuous. In most of the applications, it will be continuous. So the wave function is something that's continuous in space. So that's a very important property that if we find solutions that's not continuous, that does not represent the physical system somehow. And we also learn from that the system, actually, when we started with the wave function, with the Schrödinger equation, the solutions will provide us, together with the solution, will provide the energy that normally we call eigenvalues. And the eigenvalues and the eigenfunction is something that characterizes well the system. Well, we are not really enforcing those terms because we want to go more in the fundamentals, right? And once you know the fundament, you can have the notation. You can use the notation that is you please, because then it's just notation. It's a way of expressing things. Okay, so let's continue this lecture. Starting with the Schrödinger equation. And I wanted to make a sentence here, that the Schrödinger equation is for quantum mechanics what the Newton equation is for the classical mechanics. So basically, there is no way of dealing with classical problems if we don't use the momentum transfer, the external force, the mass, the inertia. Here too, we have to work with those concepts. And those concepts, they are very important. And we came with a time-independent equation that is a time independence, but if the potential has no time on it. The solutions do not move in time very easily. So we call time-independent Schrödinger equation. So we end up by having this nice equation that we could not deduce, but we try to put in a way that you understood how Schrödinger came with such an idea, very important idea. And then now that we know the equation, we're going to consider many physical systems. Normally, in a physical system, we know the potential. We know what are the external environment, how the external world acts in this particle. By that I mean that like a particle trapped in a box, a particle held by a force, a Coulomb force, making the atom and things like this. That's characterized the physical system. So we have this. Normally we know the potential. And knowing the potential, we go to determine the energies and the functions. And once we have the function, we make interpretation. Right. So this is mostly what we do in quantum mechanics. And then we're going to start to see phenomena that normally we don't see in the classical mechanics. And today in special, we're going to deal a little bit with the tunnel effect. It's an effect that really is very present. Today we actually start to solve the problems, show the fundamental and the application. Where is that in bio things, including bioengineering? Right. So let's then get familiar with the way to solve the problem. And while I'm doing this, we're going to also start to highlight new properties of this wave function that we're going to have to know for the next steps of the course. Okay. You know, in quantum mechanics, we have two types of systems. The ones that are confined, we call bound system, and the ones that are not confined. A particle comes from the infinite, interact with the system and goes back to the infinite. The first one is called bound states, right? And the second one is called scattering states. They both are very important because they both characterize a lot of things in the physical system. So we're going to start with a bound system. So we localize the particle, and we know many implications of localizing a particle. We're going to do an example that's a particle in a box. We have a rigid wall box. Rigid means does not deform and doesn't change the shape, right? And we put a particle, a massive particle, inside. So we have a particle of mass m, which is inside. And of course, a classical view of the problem is that the particle keeps bouncing. If I give some energy to the particle, it's bouncing anywhere. Classically, you're going to say that, well, one state is the particle really at rest inside the box. But that doesn't exist in the quantum mechanics because, as we saw, the uncertain principle do not allow that. Because you have a confined, you determine the space means you gotta have some momentum. Cannot escape from that. Right? Okay, so what we have in this problem that characterize the physical system is the potential. And the potential of a box is such that there is no real interaction while the particle is in between the walls. So we call zero when you are in between the walls, x less than L, bigger than 0. But that is infinite. And the reason we put infinite, the potential, is that it's unpenetrable. You cannot go beyond this point. So for x bigger than L, or x smaller than 0, the potential is infinite. Particle cannot be there, right? So for x smaller than 0 and bigger than L, the potential is infinite. That's the way to represent a rigid box in the quantum contest. And then we have two ways of, we have two regions of space. In fact, in the quantum solution of many problems, we divide the space in different regions. And then we connect them because we know the wave function has to be continuous and so on. And we know the interpretation. So if we don't want the particle to be in some place of space because it's not allowed for many reasons, like an infinite potential, we do not have a wave function there. The wave function has to go to 0 at that part. Good. So then, the potential acts in two different parts of space. So the equations. So we have an equation for the inside part of the box, and we have an equation for the outside part of the box. The outside part of the box is a trivial solution because the wave has to be 0. There is no possibility for the wave to exist in an infinite potential. That's true. That's a true. Then that's part. Anything outside the box, the wave function has to be 0. Right? Because the potential is infinite. If the potential was infinite in one point, we're going to learn later that that may not be true. But here, the potential is infinite in a whole space. Then it is impossible for the particle to exist there. If the particle is not there, the wave function is 0. But then that is the inner part. And the part inside the box, we get a kind of free wave for the particle because there is no external force during this region, right? The particle will fill the box only at the walls. So we have the minus h bar squared divided by 2m times the second derivative equal to the energy times the wave function. So we gotta find what's the wave function and what are the energies that complement this kind of thing. But remember, we have the 0 function outside. So at the turning points, which is 0 and L, the wave function, which is continuous, has to be inside and outside 0 to be continuous. So that's the problem. That's the most simple problem we can do it, right? And what's the difference of a free particle and the particle in a box is that the box has a restricted space for the particle to exist. And we have to respect that. Okay, so let's then consider this and solve the problem, right? And the solution of this problem is kind of nice because I'm going to rewrite the wave function. So we take the wave function, we rewrite the wave function, we just take the energy and put it to the other side, multiply by 2m divided by h bar square E. So what we are looking for is an equation that has a solution, this part. It's like this. You know, you learn from mechanics that there are a class of functions that if you take the second derivative and add it to the function, there is a way of giving 0. Those are the oscillatory functions. So we're going to call this k square because the energy is positive. So for us, k square is equal to 2m E divided by h bar square. Then the equation is actually the second derivative of the function plus k square psi equal to 0. And that equation has a solution, sinus and cosinus. Sinus and cosinus of this constant here, right? If I take, let's take cosinus. If you take the first derivative, you get the sine with the opposite sign. And if you take again the derivative, you get another k. You get a k sine, and then you're going to get another k cosine. So I'm going to have minus k square cosine plus k square cosine, which is 0. Equivalent for the sine. So we have sines and cosines as solution, and this is, you can verify, right? So the solution of this is, that's the harmonic oscillator type of equation, right? And we know that the solution must be oscillatory. But now we have to impose the conditions. It must be zero, always be zero. Doesn't matter the value of k, that must be zero at zero and then at L. And the way for this to be zero and at L, the A has to be zero, because cosines of zero is not zero. So, and the sine is zero, so I have at least one point when this doesn't hold. So this part of the solution does not apply for this situation. Therefore, A is zero. So I have only the sine b times the sine of kx as the solution. So the solution of this equation, obeying these boundary conditions, is sine b times sine of kx. And k is this quantity here, which is related to the energy. And now we know that A is zero, so we take this out. Of course, naturally, sine of zero is zero. But now I have to make sine of KL equal to zero. And for that to be true, I cannot have any k. I have to have k's that multiply by L, give me some argument for the sine, that's zero. And this is an integer number of pi. N equals to 0 is the trivial. We don't want n equals to 0. So for n equals to 1, 2, 3, integer number different of 0, this is true. So you see, I found a solution, and the solution is b sine, this is the solution for the wave, but the k must be such that KL is equal to NL. So you see that this physical system that I just showed to you, following the Schrödinger equation, it shows only a few possible values for the energy, because a few possible values of k. This is all constant. The mass of the particle, h bar, they are constants, right? So the only thing that can obey this is the energy. So by implying this condition, we know k square L square is equal to n square pi square. I just square this relation, and in the place of k square I put the term that depends on the energy, and I got discrete set of energies for this problem. And those are the possible energies. My particle in a box cannot exist following the quantum mechanics in any energy. It must have a discrete set of energies. And of course, the solutions, we know that k has to be n pi divided by L. Therefore, the solution is b, which is a coefficient, times sine of n pi divided by L x. Those are the functions, those are the solutions for the problem. And we know something extra. The particle psi square represents the probability of finding the particle somewhere in space. But the way that we set the physical system, the particle must be here. So the integral from 0 to L must be 1, because I am 100% sure that the particle is in that part of space. Therefore, the integral from 0 to 1 of psi squared dx is equal to 1. That integration of sine everybody knows how to do. You can get what is the b that satisfies that condition. So normally the coefficient is a coefficient that is not free. It must obey some other of the properties of the system. So here we are with a particle in a box. Quantically, mechanically speaking, there are some energies that I can have. and n is equal to 1, 2, 3, and so on. So there is a discrete set of energy, and there is a discrete set of function that make the system to exist. So in the quantum mechanical point of view, you cannot localize an electron, even in a tiny little space, for any energy. You have discrete energies for that, right? And that's very important in many applications. Electrons, or even other particles like protons, H plus is everywhere in the life science. And they must be localized. They must be somehow discrete in energy, and only a few solutions exist. This is very interesting because we're going to explore that on the chemical bounds of big molecules to understand what are their colors, why they have what they have, how they behave the way they behave, how is the reactivity if I make the electrons to delocalize or to localize. The solution of the box normally is very important for all of that. And we're gonna do in the coming lectures what I call the bound system. And then we're gonna be able to solve that. Now, in quantum mechanics, it's very nice to create diagrams to visualize what we got as solution, right? So for the box, we got many solutions, and I could represent the energy of the solution. So let's first look at this diagram. This diagram, I'm putting the energy. This is an energy scale growing up. And 0 is not solution for the particle confined in this box. But n equals to 1, I have an energy level with some value, h squared divided by 8ml squared. Right, that is a pi there that when we make KL equal to any pi, then the pi of the h bar, when we square these things and everything, it comes with cancel. Okay, and then n equals 2, we have another one, and n equals 3, we have another one. And if I represent what are the functions that I have here, for the fundamental state, we saw that we have only a sign. A sign, if you remember, a sign where KL is equal to pi. So that means a stand wave, which wavelength, right? Remember that K is also will be basically the momentum of this. So we have a half of a wavelength dividing this box. We already discussed this, like when we agreed that we had wave interpretation for this. And I put this dashed line because look, you still have the time. This is a wave, really. So this is the amplitude, right? That's the spatial part. But this is oscillating in time because remember we saw that having energy, we oscillate in time. So that's why I kept the dashed line to fill it up. And this is like a wave in a string, as we discussed. That's why we discussed in the beginning that nice composition of waves and everything. Now, the next wave, so this is oscillating here with this amplitude distributed along the x. For the second energy state, we're gonna have a full wavelength in this system. It comes to here, and again, dashed line, because actually the wave itself it's oscillating, right? So actually, the wave is like this, and the wave square, of course, will be something different, because when you do the wave square, the modulus square, we get mostly the amplitude, because the energy is just a phase. Remember, when I don't have time dependence on the potential, the wave function has a time solution, e to the minus I E divided by h bar t. Therefore, when I multiply by the complex conjugate of this to get the modulus, the time independence goes away. And I end with only the spatial. Equivalent here. So if I go to the third state, that's teaching us something very interesting that we already learned. As I increase the energy, the momentum is also increased. The momentum increase, we are decreasing the wavelength. So we are able to match more wavelengths in this box. Increasing the energy for the particle in the box means that we are increasing the energy, means we are increasing the momentum. Therefore, decreasing, remember the wavelength is h divided by the momentum. And the momentum is the root square of the energy for this case. We want to go and take the modulus square, which is the probability distribution. And as you can see, when you have confined things, you have many nodulus of this. You have many tops, many maximums on the wave, but you have also zeros. Huh? And when I take the square of this, I get what I'm showing to you here. And that's the density of probability, right? If I keep finding the particle in this system, I'm going to find, when it is in the minimum state, mostly the particle at the center. And very little, almost zero, not almost, basically zero at the walls, but tiny little bit at the closing to the walls. That's the real space occupation. If I look into the first excite state, this is the fundamental state, this is the first excite. If I look into the first excite state, what I get is very interesting. I have a nodulus at the center. So the particle actually will be distributed in probability on both sides, but not at the center. Right? So it will be these two blocks. And further, if I go to the third state, the distribution probability of finding the particle in the box goes like this. You see that as I increase the energy, the number of those lobes will increase and increase and increase. If I go to very high quantum numbers, if I go to a very high quantum number, probably what I'm going to get for a very high quantum number, this is here I'm going to represent very high n. So a very high quantum number. What are we going to get when we go to a very high quantum number? Well, you know, we're going to have here the box, and we're going to have these things oscillating so many times. The probability distribution. That's almost like occupying everywhere more or less equally, which is what I expect from classical mechanics. So normally when we go to very high moment, very high energy, very high quantum numbers, we're going to get situations that remember us from the classical mechanics. This is a characteristic of the quantum systems, right? When we go to very high momentum, very high quantum numbers, we get remembrance. We get things that remind us from the classical. So that's, you see, that's just the particle in a box. It's so rich. Now, that is something interesting I would like to show you, that the energy separation of the levels, because as you're going to see, when I have electron confined, I can come and shake. Imagine I have this box. If I somehow make this shake, I may end in this transition. I may end, in this state. And this is a transition, right, of states. And that will be very, very possible. We're going to learn that in another block of our system. It's possible the system to go from one state to the other. And of course, it changes completely the distribution. Right? So we must have ways of deforming the wave function by external field in a way that we provoke the transition. And it's not in any way, right? If I come and only make this in here, I may not do it. I have to do in a way to distribute the probability, and that will give origin to we call the selection rules. That's very interesting. We're going to learn all that. But there is one thing here I wanted to remind you, is that the energy separation is observable when L is small. Why? Because the energy goes with L squared. If L is very big, these levels will be so close to each other because we are divided by a big number. That is hard to observe. So when we come to the macroscopic world, if I have a box this big, like my hands, and I put the electron, L is so big that probably I have a hard time to observe those levels. They'll be too close together. But when we are in very tiny dimensions, that's not the case. When we are in tiny dimension, the energy levels became very well spaced and we can observe. That's why many confined electrons in the atomic level, they show discrete spectrum. They show energy that are discrete for us. And now we can calculate what is the distance between two consecutive levels. We just take the energy, as we learn, remember, the energy is equal to n squared, which is 1, 2, 3, 4, an integer number, h squared divided by 8ml squared. I was telling you that L is what make the system well spread, the levels or not. So a macroscopic type of confinement normally do not let you see the tiny little space between the levels. But if this is small, it's compatible with the atomic size and things like this. That happens that this is a macroscopic observable. We can see actually that the electron in that configuration will have only a few states. Very well, and then by calculating the space between the energy levels, we get this relation. Just take this for n plus 1 minus the 1 for n, and we get this. And if I take the minimal state, n equals to 1, so I ask the question, when we go into the first state, to the ground state, that's the lowest energy state, to the first state, what is the energy we need? And we get this value here. We get that this delta E is actually given by this number. And as you can see, is inverse proportional to L. That is very interesting. I'm going to use this model later on to show to you that this is mostly of the energy we observe in macromolecules. When I have no freedom for the electron to be spread, L is tiny little bit. It's small. And if it is small, this energy is big. And that goes to the ultraviolet. When this is small, I can see, comes to the visible or even the infrared. So depends on the localization of the electron. We start to see things in different ways. Okay, now, you see everything for one localized electron. We're gonna come back to the localized electron, to the bound states of electron, models of molecules and everything, how the electron behavior in that case, in the coming lectures. But now we're gonna go to what I told you, scattering types of problems. We're gonna do scattering. it means electron comes, interacts with a situation and goes away. And we want to understand what's happened there. We want to understand one of the most important phenomena for quantum mechanics in general, which is the tunneling effect. And there are many other aspects of the quantum mechanics, like coherence, I did not touch yet, because we're going to build up and then we're going to come to this concept later. Okay, so I would like now to start to discuss a problem that is electron has to pass through barriers. There are so many barriers in everywhere, right? The box was an impenetrable barrier, but sometimes the box is penetrable. And what's happened in that case? What wave has to tell about those things? Then we have to remember a little bit about wave and optics. Even if the index of refraction is very high in some medium, you still can have penetration of light. And you have a lot of reflection, but you can have a penetration. And that's true also for the quantum mechanics, because quantum mechanics basically deals with those waves, right? And this is what we have to do now, is consider the electron in a situation where it comes, interacts with the system, and goes. And we want to see what effects are there. And the first effect I want to solve is what I call the finite barrier. We're going to do many examples on this, but the finite barrier is something important. So I want to do that. I want to see an electron that comes and see a wall, and then it normally will bounce back classically, but quantically may pass through. And by passing through, it means that electron can be transported even in situations where classically it could not be. And thanks to that is that we have many transport phenomena in nature, especially like photosynthesis, like mitochondrial respiration and everything. And that's a very interesting effect that we shall concentrate on and get interpretation for that. Because this is so important phenomena, I'm going to start this topic on the next lecture. So, see you next lecture.